Shall we? Okay, let's get started. All right, this is, I guess, the review/discussion session. So, any questions on any topics? I'll take the conceptual ones, and then we have a plan for continuing the homework questions, which are essentially past exam questions, actually, if you haven't noticed. Some of them, not all of them. Some of the really tedious ones are not really exam questions. But let's take a look at where we are. That's you guys can see it, right? So basically, I think to specify things exactly, the exam will cover anywhere until the end of week 7. So lecture 13. You're not responsible for this exam for lecture 14, but clearly this discussion session talks about stuff between lectures 1 and 13, so it's probably good to review that discussion session. But they're not going to be responsible for anything we've covered starting from week 8. Does that sound good? Okay. And the exam can come from any concepts or the labs. As I said, I'm not going to test you for memorization, but you should probably know what sequential consistency means. Not for this exam, for the final. Or LRU replacement. Hopefully you'll remember what that is, least recently used, right? Okay. Any conceptual questions? Anything that you want me to go over topic-wise? Everything is good? Yeah? So should we solve questions then? Do you prefer that? Yes. Okay, sure.
So as far as I understand, the agree predictor is using the things that is previously, but pouring it into another bit, shows the likeliness of whether the prediction is taken or not taken.
Yes.
But if it says it's not taken, at the end of the day, I guess we don't take it.
So the idea of an agree predictor, just to make sure everyone is on the same page, is you don't directly predict whether it's taken or not taken. Well, in the end, you make that prediction. But because branches are biased, you set a bias bit for each branch. Let's assume that you determine it statically. And the goal is to reduce the negative interference. Different branches can map to the same prediction entry. Assuming branches are biased, you set a bias bit for each branch. And the agree predictor, the idea is to predict whether the branch direction agrees with that bias or disagrees with that bias.
So what happens if they disagree?
If the agree predictor disagrees with that bias, then basically you predict it, so your bias may be taken. If the agree predictor says, I disagree with that bias based on the history that I have, then you predict it not taken, right? So if the bias bit says this branch is highly biased to be taken, and the agree predictor says, oh, I disagree with the bias at this point in time, you predict it as not taken. Now that prediction may be correct, right? So at the end of the day, you update the agreement or disagreement with the bias. You don't update the taken or not taken outcome. Have I consistently agreed or disagreed with the bias, basically? Does that make sense? And as we've seen in, actually, maybe I can bring up that over here very quickly. Maybe we should do the PDF. Oh, boy. Maybe we should not do the PDF. Okay, anyway, if you go to branch prediction, I cannot see anything here, but I'll search for agree over here. There you go. We had an example over here. Basically, if both branches are biased, what happened there? That's interesting. Let's go back. This is an example of wasting network bandwidth. These things waste energy in the world. Okay, basically, if you see in this example, if both branches are biased, and they happen to map to the same entry in the baseline predictor, you will get a lot of mispredictions, right? Because they're biased in the different ways. But in this case, if the bias bits are set correctly, they will update the agree bits in the right ways. Basically, most branches will agree with the bias all the time, assuming bias bits are set correctly. So the predictor will almost always agree with the bias. As a result, when the two branches interfere with each other in an entry, they will all agree, right? Does that make sense? That's the key insight, basically. Even though they may go a different way, if you set the bias bits correctly, you keep training the predictor with agreement. As a result, you'll get much better prediction accuracy in the presence of interference. Okay. Any other conceptual questions? We'll go back to the topics here if I can. This is very cumbersome. Let's try this. Oh, there you go. That's better. If not, we'll start solving questions. Going once, twice. All right, it's time for questions.
How do you freeze the autofocus? This one? Okay. So last time we started with homework 3, and we solved everything until question 5, and now we will continue with question 5 here, which is about fine-grained multithreading. So probably you still remember the question, but I will quickly go over it. So we have machine 1 with 5 pipeline stages, which are fetch, decode, execute, memory, and write back. Each stage takes 1 cycle to execute, and here we assume a data cache with 100% hit rate. So basically, we never stall on a cache miss in this processor. We never wait for a main memory access. Branch directions and targets are resolved in the execute stage. So branches are over here. And pipeline stalls when branch is fetched until branch is resolved. Dependency check logic is implemented in the decode stage. So here we check for dependencies. And if there's a dependency, since there's no any forwarding path, the processor again stalls on dependence. Okay, so to avoid these stalls, we will consider modifying machine 1 to use fine-grained multithreading. So, and the first question is to implement fine-grained multithreading in this pipeline. What kind of changes we need to make in high level? So obviously, since we will have multiple contexts, right, multiple threads working here, each of them should have their own program counter, right, to fetch the next instruction. So the first thing that we will need to do is duplicating those PCs over here. So we'll have multiple PCs. And then, okay, so here we have multiple PCs, but on each cycle, we'll need to select which of those PCs to use, right? So those PCs will be connected to a multiplexer, and the control of this multiplexer will be basically the thread number, the thread ID. Right, and based on which thread we want to select next, it will be given as an input to the multiplexer, and that corresponding PC will be used to fetch the next instruction from the instruction cache, which is over here. So we don't need to duplicate the instruction cache, right? So it is unified. Okay, so this is what we need to add in the fetch stage. And then in the decode stage, again, since we have multiple threads and each thread has its own context, and those registers will have their own values, we'll need to have multiple register files, right? One for each thread. So I will put RF here. So you'll need to have multiple RFs, right? And again, depending on which thread we are executing in this stage, which instruction from which thread we execute in this stage, we will need to use that register file. So for that, to select the register file, we can have some kind of demultiplexer here, demux, right? And then to forward to choose the value that is being read from the register file, we'll have a mux. And all of those are controlled by the thread ID. Yeah, so besides the fetch and decode stage, we don't need to make any other changes, right? So after the data is fetched from the register file, from the corresponding register file of that thread, it will be executed on the execute stage in the ALU here. We don't need to duplicate the ALUs because we never will have multiple instructions here with fine-grained multithreading. And then we don't need to make any changes in the memory too. And in the write-back stage, basically, again, we should use some kind of demultiplexer, basically reuse what we have here to write to the register file that corresponds to the thread that is being executed on that stage. Yeah, so basically those are the changes that we need to make to enable fine-grained multithreading. Okay, so the next one is the machine designer first focuses on the branch stalls and decides to use fine-grained multithreading to keep the pipeline busy no matter how many branch stalls occur. What's the minimum number of threads required to achieve this? So basically here the minimum number of threads we will need will be the threads that can supply instructions during the stall cycles, right? So if the branch is resolved here, we will need to have an instruction to execute in the decode stage and in the fetch stage, right? So besides the thread that is being executed here in the execute stage, we will need to have threads to fill instructions for the decode stage and fetch stage. So it is 2 + 1, 3 threads in total. That is the minimum that we need, right? Because the branches are resolved in the execute stage. Yeah, and basically the reason is what I already explained. And then C, the machine designer now decides to eliminate dependency check logic and remove the need for flow-dependent stalls. And again, the question is the same: how many threads we need to have in this fine-grained multi-threaded pipeline? What is the minimum number of threads? So here we don't have a flow issue, right? So what the default pipeline does here is when it detects a conflict in the decode stage, a dependency in the decode stage, it stalls the instruction fetched here for 1 cycle in the execute, 1 cycle in the memory, and 1 cycle in the write back, right? So we have, three cycles in this side, which you need to fill. So basically, if there's a dependency, if you have an instruction here, so basically after after this pipeline detects a dependency, the instruction that we have a dependence to needs to complete the write back stage, right? It will need to write to the register file because this pipeline doesn't implement any forwarding paths. So if we have here an instruction from thread 1, let's say, we'll need to have another independent instruction from another thread in the memory. We'll need to have another independent instruction from another thread in execute stage, right? And here in the decode, also to be able to decode and basically to be able to read from the register file, the instruction here also needs to be from an independent thread, right? But for fetch, so this is for fetch, we can again go back to the instruction from thread 1, right? Because it won't have any dependency issues. It is just accessing the instruction cache for getting the next instruction. So basically the minimum number of threads that we will need to have for that reason for eliminating dependency checks will be 4. Okay. The rival designer is impressed by the throughput improvements and the reduction in complexity that fine-grained multithreading brought to machine 1. And this designer wants to implement fine-grained multithreading on machine 2. And this is, and those are the stages and the latencies of each stage in that machine 2. So fetch and decode stages basically the same. They are one cycle, basically one stage. They consist of one stage. And execute stage has 8 sub-stages. So it is like pipelined 8 stages. And then memory is 2 stages and write back 1 stage. And here we have pretty much the same questions as for the first machine. So the first one is to eliminate the branch-related stalls. Does machine 2 need to implement to have more threads, right, compared to the first machine? Or is the number same, not different? But yeah, it asks if it's the same. And here the answer will be the answer depends on which stage the branches are handled, right? On which stage branches are resolved. And here that information is given in this row here that branch direction and target is resolved at the first execute stage, right? So it is the third stage of the pipeline, which is same as machine 1. So here the answer will be yes, because again, the same number of threads, 3 threads, are enough to eliminate all branch-dependent stalls. And then the next one, E, what is the minimum CPI of each thread? So here some of you, I guess, a few of you found the CPI of the entire processor. So the question asked for each thread independently, right? So you need to calculate the CPI of each thread in this case, which will be 3, right? Because we have 3 threads in this case, and we can supply an instruction each 3 cycles to this pipeline. And then eventually, after filling the pipeline, we will have a CPI of 3. So 1 instruction will be retired every 3 cycles for each thread. But the overall CPI will be 1, right? Okay, so here the answer will be 3. Now consider flow-dependent stalls. Is it flow? It is data dependence, actually. data dependent stalls. Does machine 2 require the same minimum number of threads as machine 1 to avoid need to data dependent stalls? So for machine 1, it was 4, right? We needed 4 threads here to tolerate the latency of writing back the data. So basically the distance between decode and write back was 4 here. So now the minimum number of threads to eliminate the stalls due to data dependence will be, again, the distance between the write back and decode. So if you look here in this table, between decode and write back, we have 1, 9, 11, 12 stages. So here the answer will be no, and there will be need for 12 threads to eliminate completely the data-dependent stalls using fine-grained multithreading. Yeah, actually we need to put 12 here, and here's the reason. And then the next question is, what's the minimum CPI of each thread? In this case, when we use 12 threads. Again, since it's asked for each thread, the answer again will be 12, right? Each 12 cycles will have an instruction completed for each thread. Okay, and the last question, I guess, is, yeah, so I will summarize this. It's a bit long, but yeah, so basically here, the designer of machine 2 observes that in some cases, the fine-grained multi-threaded pipeline, the pipeline with fine-grained multi-threading support, has worse performance compared to the initial design, which didn't have any fine-grained multi-threading. And this happens in cases where a particular sequence that has no flow dependence. So this is the hint, basically, here, given for you to find the answer. Yeah, and so basically here the answer will be that if your program does not have any data dependencies or flow dependencies, then fine-grained multithreading is useless, right? So it won't change, it won't help you with performance, but it has some overhead over here, as we show. So you'll need to have some multiplexers, demultiplexers here, which can potentially increase the length, increase the time on the critical path. And this can lead to lower frequency, right? Which can eventually reduce your overall performance. Yeah, and here, for such cases, the reason is the increase in the critical path. Which determines the frequency of the pipeline. Okay, so yeah, I think in general that question was easy, right, compared to other questions. Any questions about it? Anything that wasn't clear? Okay, then I guess we can move to the next one.
Okay. Let's quickly go through question number 6. In this question, we have a fine-grained multi-threading machine. The pipeline has 22 stages and is one instruction wide. Branches are resolved at the end of the 18th stage. And we need 1 cycle delay to communicate the branch target address to the fetch stage. The data cache is accessed during the stage 20. On a heat, there's no stall, but on a miss, the thread stalls for 100 cycles. And also, we can service 16 outstanding misses. We have 200 hardware context in the machine, so we can quickly context switch in the hardware to hide the miss latency or branch latency. So in part A, it's asking that can the pipeline always be kept full and non-stalling? So as we have 200 hardware context, we can hide the latency of the branches. But in the worst case, if we have misses more than 16, we will have stall because we can just service 16 outstanding misses. So the answer is no. When we have more than 16 misses, the pipeline will be stalled. In part B, if we have no misses, is the pipeline will be full? The answer is yes, because 200 hardware context is more than enough to hide the branch latency in this question. In part C, it's asking that if all accesses hit in the cache, to keep the pipeline always full, what would be the minimum hardware context? So as the all accesses hit in the cache, so there is no thread stall due to misses. So we just need to have enough hardware context to hide the latency of the branches. So the latency of the branch is 19 cycles because in 18th stage, the branches are resolved, and also we have one delay for communicating. So when we can reduce the hardware context to 19, which is the minimum requirement. In part D, it's asking that if all accesses miss in the cache, what is the minimum changes or requirement for the machine to not stall? So basically, because we need to hide the latency of the misses, so because the miss latency is 100 cycles, we need at least 100 hardware context to hide the latency. In addition to that, we also need to service 100 outstanding misses. So we need to increase the capability of supporting 100 outstanding misses, and we can reduce the hardware context from 200 to 100. Yeah, that's it. Any questions? Yes? In part D, you are asking?
Yeah, part D.
Okay.
We have 100 threads, and if there is
Uh-huh.
at the
Actually, when we have a cache miss, the latency, the stall cycle is 100. Yes. So if we have 100 ready threads, we can schedule them for the execution to hide the latency. Mm-hmm.
right now, and then the next 99 stages, extra 99 threads also reach the next stage, and then the 101 is the same. The next instruction for the first thread,
Mm-hmm.
which is now in the if stage, and then the next instruction, the cache miss is served, so the data is in write back stage.
Actually, I couldn't understand your question. Anyone can help? You understand? Can you repeat?
Basically, what you're saying is there are additional stages that are in the pipeline. Actually, I don't remember. I cannot read the question from here, so I don't know how it's formulated.
Mm-hmm.
But if there are additional stages like that, then if you write your assumption, I don't see the question, unfortunately. But if you write your assumption, if you say that, oh, there are 2 additional stages, so there needs to be 2 more, so it's under 2, then you will get credit for the question. So I think whenever whenever there's ambiguity in the question, or if you have some reason, please write your assumptions in the exam. I could give you a better answer if I could read the question.
Mm-hmm.
If there was data forwarding, I think
Okay.
So if there's some information that's missing
Yeah.
that is relevant to the answer, definitely write your assumption and say that's the reason.
Yeah.
Okay, let's continue with question 7 about branch prediction. Okay. So this question says that we have the following code, the following piece of code. The large array that is being accessed is completely populated with random positive integer values. And as you can see, in this code, we have 4 branches. We have B1 in the for loop, and then we have B2, 3, and 4 in these if conditions. So the first part A, ask about local correlation in these branches. And it says, of the 4 branches, list all those that exhibit local correlation, if any. So as you can see, the only one that exhibits local correlation is B1. That's not the case for B2, B3, or B4, because the fact that in one iteration, one of these 2, 3, or 4 branches are taken doesn't imply that it will happen the same in the next iteration, because there's no, the values that are being read and that are evaluated in these conditions are completely random. Part B says which of them, of these 4 branches, are globally correlated. And in this case, the answer is B4. B4 is globally correlated with B2 and B3. Because in case the value that has been loaded from the array is a multiple of 2 and is also a multiple of 3, then branch 4 will be taken because it will also be a multiple of 6. So that's the first part, these 2 questions. Now the second part of the exercise tells us that we should consider global branch predictor with 1 global history registers with 2 bits and 1 pattern history table with 4 entries. And it says the page table, the pattern history table entry is incremented by 1 whenever a branch that corresponds to that PhD is taken, whereas it is decremented by 1 whenever a branch that corresponds to that PHT is not taken. So in part C of the exercise, we need to calculate the expected value for the first entry of the PHT, this first entry, after 120 iterations. So in this case, what we have to do is calculating or obtaining the probability of one branch, of each branch to be taken or not, given the fact that the previous 2 branches have been taken. So let's, first of all, let's consider what is going to be the probability that especially branches 2, 3, and 4 are taken. And what we are going to do is considering the numbers between integer values between 1 and 6. And observe that if we go back to the code here, observe that the first condition here, branch B2, will be taken if the value is a multiple of 2. How many of these values are multiple of 2? We have 2, 4, and 6. So the probability that branch B2 is taken is P equal 1/2. In case B2 is taken, that is in case the value is an even value, then we can evaluate V3. And out of these 3 values, only 6 is a multiple of 3. So in this case, the probability is 1/3. And for B4, then we will have, if B2 and B3 have been taken, we will have that 6 actually fulfills the condition, and the probability will be 1. So using these, let's say, base probabilities, now we are going to calculate the contribution of each of the branches to the value of the entry in the pattern history table. So let's first start with branch B3. So before branch B3, we are going to calculate the probability of branch 1 taken and branch 2 taken. Observe that this is equal to the probability of branch 1 taken times probability of branch 2 taken. And this is equal to 1, because branch 1 is the for loop, which is almost always taken, right? Times the probability of branch 2 being taken. That is the probability of the value being an even value. So this is 1/2. Total result is 1/2. And now we are going to consider 2 possibilities, because, as you know, the entry could be incremented or decremented. It will be incremented if branch B3 is taken, given that B1 and B2 have been taken as well. So if B1 and B2 were taken, then the values that we are considering are 2, 4, or 6. So in this case, the probability of branch B3 being taken is 1/3. So this gives us, so it is 1/3 times 1/2, which was the probability that the previous two branches were taken, right? So this is 1/6. And the probability that it is decremented is that the branch is not taken. And in this case, it is 1 minus 1/3 times 1/2. It's equal 1/3. So the net contribution of this B3 is, sorry, this is minus, it's 1/6. Oh, sorry. Thank you. It's minus 1/6. So this is a contribution of B3 to the final value of the first PhD. Now let's go for B4. So for B4, we will first need to calculate the probability of the previous two branches, B2 and B3, being taken. So, and this probability, as you can see here, is 1/3. If branch 2 was taken, the probability for branch 3 being taken is 1/3. So we have 1/2 times 1/3 is 1/6. If both were taken, the probability of branch 4 to be taken, branch 4 being taken if 2 and B3 were taken, it's equal 1. So this gives us a contribution 1 times 1/6 is 1/6 for branch 4. Now, next branch is branch 1. And for branch 1, we just need to calculate the probability of branch 3 and branch 4 being taken, and this probability is 1/6, because these two are only taken if the value is equal 6, so the probability is 1/6. For the branch B1, it is always taken, so the net contribution here, it's also 1/6, or 1/6 times 1, okay? And finally, for branch 2, we first compute the probability of branch 4 and branch 1 being taken. This is 1/6 times 1. And then, as we did for branch 3, branch B2. So, and then as we did for branch 3, we have two possibilities. Branch 2 being taken, or branch 2 not taken. So, in both cases, actually, because this is branch 2, the probability is equal to 1/2. So the net contribution is equal to 0. So now, if we want to calculate, in order to finalize the exercise, we want to calculate the net contribution of one iteration is minus 1/6 plus 1/6 plus 1/6 plus 0, which is 1/6. This is for one iteration, right? And so we have to do this for 120 iterations. So after 120 iterations, given the fact that the contribution of each of them is 1/6, we obtain that the final value of the first entry of the PHT is equal 1. And that's all. Do you have any questions? Okay, then we can continue with Lois.
Okay. So this question is also about branch prediction. So, so we have this loop here in assembly in MIPS code. That what basically does is storing in memory the content of this register R1. That is. We are storing in the address 4000. When we update, the loop updates this address for the next iteration. Here we set some condition to go to execute this part of the code or this part of the code. So this condition, is an AND between R1 and R2. R2 is fixed, is 1 always. We don't modify R2 in all the code. So this depends on the content of R1, that basically is if R1 is odd, we don't take the branch, the next branch. So these two pieces of codes are almost the same. We are basically updating the condition here, R1, for taking the branch or not, and then we are decreasing R5 and R5 here in this case, and R7 here in this other case. So the initial values are 5 in both. So so this branch is going. This branch is going to. So in the first iteration, this branch is not taken. So the first iteration, this branch is not taken. The next is taken, not taken, taken, not taken, because we are switching we are modifying the value R1 in this sense. So we execute this loop 9 times, taking, not taking, taking, not taking, until we set this R7 to 0. In that case, we finish the loop. So we have some latencies here. The store takes 3 cycles to execute. The add, immediate add 2, the AND 3, and the branches 1. What else? Data forwarding is used wherever possible. Instructions that are dependent on the previous instructions can make use of the results produced right after the previous instruction finishes the execute stage. And the target instruction after a branch can be fetched when the branch instruction is in store stage, like in this example. So the first question is, how many cycles does the above loop take to execute with no branch prediction? If there is no branch prediction. So we'll take this. So with no branch prediction, we have this. This is the solution, okay? So this is the store. Yeah, the fetch, the code, 3 cycles for execution, and then the store stage. The next instruction is the add. We pipeline the add in this way, so you have this fetch, the code, execution 1, execution 2, and the store. In this case, both store stages can be executed in the same cycle, because in the store we don't really write in the register file, so this the store bypasses this stage. So the next instruction is so this is the next instruction is the AND. So we have the same fetch, the code, execute in 3 cycles, and store. And then we have the branch here, branch equal. So here in the branch we have a dependency with R3. So we have to wait for the previous instruction to solve this, to store this value. So we have the fetch, the code, and we have to stall here, waiting for the value of the previous instructions, and only in that point we can execute and then store. In this case, no branch, this first branch is not taken. We go to this part. And we don't have branch prediction. What it means that we have to wait for the branch to determine the next instruction. So we only can do the fetch when this branch is finished. So we fetch the code, execute, and store this add. Then the next one, again, this is the next add. And the last one is a branch that depends on the value of R7 here. So we install here, waiting for the value, and we execute and store. So this is 15 cycles for the first iteration. For the next iteration, we have only 14 cycles, because the fetch cycle of the store instruction can be overlapped with the store stage of this branch. Yeah. So we have this total number of cycles. That is 15 for the first cycle, 14 for the other 8 iterations of the loop. So my next question is, how many cycles does the above loop take to execute if all branches are predicted with 100% accuracy? So now we have branch prediction, and it predicts always correctly. So, so we have here, so for the first iteration, we have the store, as always, the add, the AND, nothing special until here. Now we have the branch, and we have a dependency, so we install here, And then we have perfect, we have branch prediction with 100% accuracy. That means that we are going to predict this branch always. So we are always fetching the right instruction here. So that in this case is the add. So we don't have to wait until this branch resolves. We don't have to wait until here. And then we can fetch, so we fetch the next add, but we cannot decode it because the decode stage is occupied by this previous instruction. So on the next instruction, we can, that is an add, we can only fetch it when the previous instructions move to the decode stage. Yeah, and then we have the other branch here. That is, as always, it depends on the previous instructions, have some stall cycle here. So here is 13 cycles for the first iteration. For the other iterations, we'll have 3 less cycles because if we execute against the loop, we have the fetch stage here. We install here the code, execute 1, execute 2, execute 3, install. So we are saving these 3 cycles in consecutive loop iterations. So in total, you have 13 cycles for the first iteration plus 10 cycles for the other 8 iterations. So the next question is, where is the next question? Well, the next question is, how many cycles does the above loop take to execute if an static backward taking, forward not taking branch prediction scheme is used to predict branch predictions? What is the overall branch prediction accuracy? What is the prediction accuracy for each branch? So this means that we are predicting backward taking. So this means that this branch and this branch are backwards, so they are predicted taken. These and these are predicted taken. And this is forward, so it's predicted not taken, always, statically. So in this case, we have this. So this is the store, the add, and so this is always predicted this is the branch. Okay, the same, it waits for the previous. And now, in the first iteration, this is always taken. We are predicting, our predictor predicts not taken, so we have a misprediction. So we execute the next instruction after solving this branch. So we mispredict, so we probably execute this instruction here, but then when we resolve the branch, we flash it and we fetch it again. Yeah, and we fetch it here at this point. Okay. So the first iteration is misprediction. So the next instructions are as usual, add the branch. So this is how much? 15 cycles. What happened? This is in the first iteration. Or in the if the branch is predicted. If the branch is predicted correctly, what we have, instead of having this, we will have something, instead of having this here, we'll have something like fetch the code execute one here. So we are saving 3 cycles here. If this is predicted correctly, correct prediction. So yeah, so in case of this branch, we have so the first iteration is mispredicted, and the other 8 predictions are well predicted with the correct prediction, and other 4 with misprediction. So yeah. So yeah, as explained before, so the number of cycles taken by an iteration when this branch is not predicted right is and we have another thing. So this is only the first loop. Then in the next iteration of the loop, we will overlap with the previous loop. So we have fetch, decode, execute 1, execute 2. So we are the first mispredict loop is 15 cycles. The in subsequent mispredict loops, we have 3 less cycles. So we have 12 cycles for mispredicted loops, and for predicted loops, we save 2 more cycles here. We have 10 cycles and 12 cycles. So the final number of cycles is 15 for the first one, and then 4 mispredict cycles and 4 correct predicted cycles, not loops. 4 mispredicted loops and 10 for correct predicted loops. So the accuracy is like this. So in this case, this loop is this branch is executed 9 times. So we have 5 times. So the first time is always mispredict, and in the 8 other ones, 4 is predicted correctly, and the other is mispredict. So we have 4 out of 9 of accuracy. And in the first of this do it branch, we always the first one is always predicted correctly, and this one is always predicted correctly, except in the last iteration when R7 is 0, so we don't take this branch, and so this is mispredicted. So we only mispredict the last in the last iteration of the loop in this case. So on the total, if you do the count, the total misprediction, the total prediction accuracy is this number. So you have questions? Okay. Question 9. This is about interference in two-level branch predictors. Let's read the question. Assume a two-level global predictor with a global history register and a single pattern history table shared by all branches. This is our predictor A. So in predictor A, all branches share single pattern history table. Question 1. We call the notion of different branches mapping to the same locations in a branch predictor branch interference. Where do different branches interfere with each other in these structures? So as discussed in the class during the lectures, the interference happens in the pattern history table entries, where we have different prediction results for different branches. The second question is, compared to a two-level global predictor with a global history register and a separate pattern history table for each branch, which we call predictor B, we want to answer three following questions. First, when does predictor A yield lower prediction accuracy than predictor B? So it happens that this case happens when, for different histories, for different branches, we have two opposite directions for the branch. One, for example, branch A is taken and branch B is not taken. And the most severe case is that we have one always taken branch and one always not taken branch, referring to the same pattern history table entry. As an example, we have this for loop here, in which we have if condition 1, in which based on the value of I, we have this branch. If modulo 2 equals to 0, we have this if value, this if loop, this if block. And the second conditional block is this, in which we compare the value of I modulo 2 against 0. Here, in the answer sheet, you see that we have two different decisions for the history n, tn. This is correct that if we have n, for this first block, first if block, if we have not taken, then the next time that we have this loop, we execute this loop, we will have taken. But for the second if block, we change the decision every two not takens. Not taken, not taken, taken. So based on this history, we may go to, based on the history NTN. So if we have NTN for the first loop, the last time we visited this loop, this block, the last time we executed this if block, we had not taken. So the next time we visit it, we will have a taken branch. If we have NTN for this block, the last time we visited this if block, we had not taken. But it is not always the same condition. We may have taken or not taken for the next time. So if we have this
let's assume that this is for if condition 1, and this is for if condition 2. So for the if condition 1, here we expect taken, but for the if condition 2, we expect taken or not taken, because this is not always taken or not taken. So these two branches, when mapped to this pattern history table entry, will interfere with each other and affect the accuracy of decision making for this special pattern history that we see in the execution of this for loop. The second question is that, could predictor A yield higher prediction accuracy than predictor B? This is possible. This is possible for the cases that interference between two different branches on the same pattern history entry will lead to a better decision for one of the loops, for example. Let's consider this example. We have one branch, B1, that oscillates between taken, not taken, taken, not taken, and the branch B2 that is always taken. And for the pattern history table, we use a single bit last time predictor. So what happens if we have two separate pattern history tables for branch 1 and branch 2? For branch 1, since we are using a single bit last time predictor, as we discussed in the class, the accuracy will be 0%. And for branch B2, it will be 100%, right? So this was predictor B, in which we used two different branch predictors, but two different pattern history tables for branch 1 and branch 2. Now let's consider the case in which we use predictor A, where two different branches, B1 and B2, share the pattern history table. In that case, for B1, we will have 50% accuracy, but our accuracy for B2 will be decreased to 50% if these two conditions are executed at the same frequency. But let's assume the case that this branch B2 is executed with a higher frequency, for example, 10 times higher, 100 times higher than B1. Then the accuracy of this B2 is also increased, and overall, our branch predictor A, which shares the pattern history table between branch 1 and branch 2, can give us a higher prediction accuracy. Here we have a pseudocode example in the solution sheet. As you see, for example, branch 1 and branch 2 have the same history. They are executed right after checking condition 1 and condition 2 for two different if blocks. And we assume that we have a 2-bit global history register. So when we execute branch 1, we always see the same history for execution of condition 1 and condition 2. And also, when we execute branch 2, we see the exact same history because we only have 2 bits for the global history register. So these two if blocks are executed, are pointing to the same entry in the pattern history table during the execution. So if we execute this block with a dedicated, this last block that I highlighted here, with a dedicated pattern history table, then since it alternates between taken and not taken, still we will have 0% accuracy. But when they share the pattern history table, due to better accuracy of executing branch 1, this branch 2 will also benefit and have higher prediction frequency. Our last question is there a case where branch interference in predictor structures does not impact prediction accuracy? Yes, that's possible. In cases that the interference of different branches that are going to the same pattern history table entry does not change our decision. For example, if two always taken branches are going to the same entry, or two always not taken branches are going to the same pattern history table entry. Here we have another example. As you see, in this example, for pattern taken, we always have taken. So there is no difference if we have separate pattern history tables for this loop branch and for this if branch, or for the case that is predictor A, we introduced at the beginning of this question, in which they share the pattern history table. Always we have taken, no change in the final decision. Any question?